if it's not too much, you can just interrupt by using your microphone and ask a question. It's as simple as that. Yeah, so predicting knee forces using Mayonado, it's Heiko Wagner et al. And the et al. Is really important here. I started to write some names and then I stopped because there are really a lot of people working here in the group, and it's a quite long list. Maybe you can go just visit the website of our department, and there's the team, and then you can see everybody. And the et al. Is also a company called Predimo, where some of our group have just funded last year, and some of the developments has also be done there in this Predimo group. So maybe you can visit that as well. So question, so predicting knee forces using Mayonado. I tried to organize the talk with that outline. What's the problem? What's the solution? What else? So first the question, what's the problem? For example, if you look at that video, it's Superman, it's a landing situation, bam. And in this case, the question is, I guess that there will be very huge forces in the knee joint. And the second question is, how large are the forces? Is it too much? Is it okay for the knee? And so if we pose that very simple question, what are the forces in the knee joint, for example, of this Superman? The question is, we have to measure these forces. And if you think about that quite easy sentence, measure forces in the human body, we must say that in most cases it is impossible. It is possible in some situations. For example, you can use some force buckles which are implanted on the Achilles tendon, for example. But in any case, you have to make a surgery. So you have to open the body, you have to place a sensor in the knee or in the hip or wherever as well. So it is complicated and nearly impossible to measure these forces. And there's only a few situations, and one of them is that so-called CAMS knee project. And you can see the paper there. It's a comprehensive assessment of the musculoskeletal system, the CAMS knee data set. It's a really, really nice study, which was conducted by the ETH Zurich and the Berlin University, Charité, I guess. Is it Charité? It's the Wolf Institute, Charité. Yeah, it's a Charité. And this was done in 2017. And here, 6 patients who got a knee prosthesis got a special knee prosthesis. So it was an instrumented knee prosthesis. So the knee prosthesis was able or is able to measure forces in the prosthesis, and with some wireless devices, you can measure the forces in the outside. And the 6 subjects were asked to perform some movements. So they did some normal walking, level walking, uphill, downhill walking, stairs climbing, squatting, and turning. And I think that was it, I guess. And maybe so it was maybe up to 8 to 10 different movements. And they were measured with a full body Vicon marker set. Not a complete marker set, but nearly complete marker set. They have the instrumented knee joint, as I already said. They measured the ground traction forces with Kistler ground traction forces. You can see that in the left picture. And with this special device, they were also able to look into the body. And I would like to show that on the next video here on the right, where you can see the subject doing a squat. And in the right corner, you see that video. So you have the kinematics, you have the full body kinematics. They have also measured EMG from 16 leg muscles. And on the right, you can see now the ground reaction forces during the squatting movements, and in the middle trace, the in vivo forces in that prosthesis. And the EMG is signal, as you can see. So this is what they measured. And it is possible to apply for that data set. So you can just write an email to this group, and it's possible after you sign a contract, blah, blah, then you will get the data. And so I have the data, and I try to use that to make some simulations based on that. But this is one of the few cases where it was possible to get some measured data during human locomotion, like walking or squatting. This is only very few data that are available in the community. So this is one of the graphs they published. As you can see, for example, on the left side, this is the extension flexion kinematics, what you easily can get always with kinematic systems. But on the right-hand side, you can see for different movements like level walking, stair descending, downhill walking, standing up, sitting down, and squatting, the different forces in the knee joint. This is the mean for the 6 subjects and the standard deviation. But as I said, it's not possible to get these information in general. So for example, during playing volleyball or a marathon or landing like Superman or what else, it is not generally possible to get that data. So what could be a solution? And now I guess that I would like to introduce that physics is the solution, as in many cases, I would say, as a physicist. So we can, based on physics, we can develop computational models. For example, the Myonado, a 3D model that we have developed here in Münster, and I will present that later on. The next 2 slides, Willem Castro, please don't look at these slides because you don't like them, but I like them. It's about some stars and planets. So what is the idea of physics? So the fundamental concept is that you need a physical system like the universe or maybe the open lab behind me. So this is a physical system where you can measure some physical quantities, for example, so-called observables. And this is, for example, the body mass, the length, the velocity, forces, and all this stuff. These are measurable quantities. Then you need to describe the state of the system that you would like to describe. For example, a human or maybe a solar system. And the most important thing, this is why I like this slide, is that we need to have some laws, force laws. For example, as you can see on the right-hand side, the gravitational force. And if you have the possibility to describe a system, describe the state of the system, and you have all necessary physical quantities, and you know the force laws between these states, then, excuse me, of the quantities, then we can also try to make some predictions. For example, the movement of the planets around the sun and other stuff. So this is physics. But now the question is, what about human movement? Is it possible to use that concept as well to describe or to predict, in some case, a human movements? And we must say, yes, it is possible. There are already some musculoskeletal models on the market, mostly to describe the force generation in muscles. You have equations that should be force laws. For example, the Hill equation, as you can see on the right-hand side, which is describing the force velocity dependency of the muscular force production. There are different other force laws. And then we can combine them to describe, for example, dynamic movements like this jump. Yeah? So this is the basic idea, to use physics in order to describe and get a better understanding about human movements. But again, back to the question, why is it necessary to use computer models, for example, to get information about the force in the knee joint, which we cannot measure normally, or for example, in the elbow joint, which is shown here. So the basic to explain the basic idea or the necessity to use models, I would like to ask what are the forces in the elbow joint if somebody is holding this 10-kilogram mass in the hand. So the first basic assumption is, okay, you have the mass, and because of the gravitation, you will have minus 100 Newton if you define the positive axis in the vertical direction. Then it is now minus 100 Newton is the force, it's a tensile force in the elbow joint because of that mass. This is if you only describe the situation based on the external view. But if you look a little bit closer to that situation, you see, okay, the mass do have an external lever arm to the center of rotation in the elbow joint. And if there are no further forces, you will get a movement, downward movement of the arm. So then, because the arm holds that mass, there must be muscles which are active to counteract this internal elbow moment. So in this case, because let's assume that the lever arm of the muscle is 5 times smaller than the external lever arm, then you need, for example, 500 newtons as the muscular force to counteract this external moment. So if you sum these two forces up, so the force based on the external mass and the muscle force, then you will get the resulting force of plus, so it's not a tensile force, it's a resulting compressive force in the upper arm of plus 400 Newton. And this is completely different to the first assumption of minus 100 Newton based on the external mass. So we must use musculoskeletal models if we would like to have some information about the forces in the body. So therefore, we need to have these computational models, musculoskeletal models, to calculate or describe that. This is a very, very recent paper. So it's just published in April 2020. And here a group of researchers used an OpenSim model, which is shown on the upper right side, to describe the forces and the muscular activation based on an OpenSim model. And they used these Kamsini data set, which I have already introduced. And as you can see on the left-hand side, you see the EMGs. So in black is the values measured during walking, and in red are the measured EMGs or forces during the squatting movement. And the solid line is the measured EMG, for example, here in this case, or in this case, it's the measured force in the knee joint. And the dashed line is the simulation based on that OpenSim model. And I was surprised, I must say, that the differences between the measured and the calculated values have been really large. For example, here you can see it's a quite large difference, or here between the red dotted line and the red line here, or here hamstrings, and even for the compressive force in the knee joint. Here you can see this blue line here. I have highlighted that is the measured force in the knee joint during a squatting, and this here is the calculated force based on that OpenSim model. And I think the factor is a bit more than 2. So therefore, I thought maybe we should work on that, because I believe that computer models can perform better than that. And therefore, because we have developed, as I already said here in Münster, the Myonado, it's a 3D computer model, and we have included 35 bones, quite similar to OpenSim, with 21 joints and huge number of muscle lines of actions, 682. And we can do this extended inverse dynamics, and we can therefore, based on the internal muscle forces and the external forces, we can sum them up to calculate the forces, for example, in the knee joint or other joints. And we have a very nice virtual reality technology to simulate that or to visualize that at the end. So this is the Myonado. It's programmed in MATLAB, SimScape, and here you can see that we can choose which joints should be analyzed. We can read in some body files or the measured kinematics. Here we can choose the method to just make kinematics or the inverse kinematics, which means that we can measure calculate also the muscle activation, or we can switch to forward mode. We can import qualysis data, ZIMI data, XSense data, FPX data, so different kind of possibilities here and some plotting tools. It's quite nice to use, I must say. So we can change the solver type and the step size and all this stuff. So at the end, we have a quite good environment to read in measured kinematic or kinetic data and then do an such an 3D analysis. I guess some of you have already seen these videos. For example, if somebody is jogging here on the force plates behind me. So based on that, we can do this full body inverse dynamics, and based on that, we can calculate also which muscle is active at which instant of time to generate these moments that have been measured. And based on that, this is what I would like to show later on, we can calculate the forces. So to validate our muscle model, so we have used a hill type model with a force velocity force length relation, also a passive force to length relation. And here you can see a paper which I haven't cited. Excuse me for that. I have to do that later on. So please ask me if you need the paper. It's a paper which is showing the behavior of the OpenZim model, and you can see measured data. The dots are measured data from different authors, and the black line is the line how OpenZim is calculating the force length and the force velocity relation, and the red line is our model, and it fits quite good. So even though that there is a difference between OpenZim and our model, our data, our muscle force length relation, for example, still lies within the measured data, for example. So, and then we used, as I said, this CAMSNI data set. On the left-hand side, you see one of the subjects doing a squat, and I used that data, so the Vicon data and the force plate data, and fitted it into our Myonado to get first that kinematics. So as I said that I already said that it is a full body marker set, but not a complete set. So for example, from the trunk, there were some markers missing. Therefore, it's a quite stiff movement in our simulation, but it's because we don't have this kinematic information. But in general, we can say it is the movement that the subject have performed. So what have we changed according to other models? I have included a new knee model, which is based on the publication of Mr. Menschik, was in 1985 or something, and I used that model in my PhD thesis, so therefore I knew that still. And it's based on the posterior and anterior cruciate ligaments, which is shown as the red lines there, the uppercase. So this here is the femur. Here I've just drawn the tibia as a box, but you can see that the flexion and extension between those two situations is a moving of the tibia along this condylus of the femur, and it is determined by the movement of the so-called forebar linkage, which is made by the posterior and anterior cruciate ligaments. Then I have included this patella. So the patella is moving on the femur condylus, and this is the patella tendon. And based on that, we can calculate the lever arms to that virtual center of rotation. And the center of rotation is the position where the two crucial ligaments are crossing. This is the physics of a four-bar linkage. So based on that, we have a more physiological description of the knee joint kinematics. It's a planar model, simple planar model. but it's now incorporated in our Leonardo model. And if we use that and calculate the forces, also based on this model, the forces here in the tibia, this is what they have done in the CAMS-knee project. It's the force here in the tibia. And then we get this graph.
Ooh.
So here you can see as the red line, this is the measured force of that subject during the squatting. It's the Z force, so it's the force in the direction of the tibia. And here are the two lateral forces, so the X and Y direction. What you can see is this thin yellow line here is the calculated force in the knee joint based on this arrangement of our Menschik knee. So here is the attachment point of the cruciate ligaments, and this is the shape. So based on this is what in the Menschik publication is used as a standard to describe this. I've used that, and based on that, we directly get a quite good description of the measured forces. There are some differences here. I think it's because of a coactivation of muscles. Maybe you can see that later on in the EMGs. But here during the squatting, it is a quite good description. It's not a factor 2, I guess. And then I changed the arrangement of the position of the crucial ligaments in the computer model. So I did so I placed that position here and here and here, and I reduced the distance here because the knee joint, which is here, is not a human knee joint, it is the prosthesis. And I asked already the authors of the paper to give me the information about the center of rotation of the prosthesis and how maybe the center of rotation is moving, whether this is comparable to that human-like situation, or is it maybe also a constant center of rotation? I don't know. And I didn't got that information. I was searching also the literature, so if somebody knows that, it would be really good for me to have that. And because based on some publication, it seems that it is completely different. Maybe it's also like that. So I made some simulations and tried to get an arrangement of that knee which better fit the measured data. And at the moment, so it's not a really optimization, it was a error searching method of my own. So this is now the blue line here is at the moment the best fit I have. So I played around with some numbers, and this is maybe which is quite good. So even at the beginning we have this discrepancy here, but then here maybe it's an overshoot here and a small overshoot there. Even this movement is there in the blue line. So the profile is quite good, but the center of rotation is not here. It's now here up there. And it's not moving. It's a fixed center of rotation, more or less. And so I'm really excited to see what is the real center of rotation of that knee joint at the end. I hope that I will get the information and we can present it later on. And then we can also, so that was, I was quite excited about that because I think the fitting is really good, I must say. And then the next step was to compare the measured EMGs. So here on the row here, you can see the measured EMGs from the CAMS knee data set. And here is the pattern of the activation from our Leonardo model. And for example, for the tibialis anterior, it's very nice. For the biceps, I must say, it's really okay. The gastrocnemius, the pattern is comparable. Here in rectus femoris, it's different. We have to discuss that. So it's two peaks here. So you can see two peaks here, but should it be like that? I don't know whether this is a good agreement or not. We have to see. Then the vastus medialis, I don't know what they are doing at the beginning here. Maybe it's the preparation for the movement, which is not in our model. But then this pattern here is very nice. And for the vastus lateralis, it's It's really impressive, I must say. So I must say the validation or the comparison with the measured EMGs with based on our predictions is really nice, I think. So we have to see, I have to do that also for the 5-hour subjects and see whether this is also true for them and how we can publish that. So two more slides in this line. So here you can see on the left the forces in the prosthesis, which I have already shown. So the Z line and the horizontal forces, and this is for the right knee. So for this subject, in the left knee was this prosthesis, and in the right knee was no prosthesis. But if I calculate for the movement the forces in the right knee and compare that to the forces in the left knee, you can see that they are around 2,000 newtons to 2,500 newtons, and on the right knee it's 3,000 to 3,500. So it seems that during the squatting movement, the subject is more using the not the right knee without the prosthesis, and he's not using the prosthesis side in that way. I would like to point, because of time is running out, to discuss a little bit the coordinate systems. So as I said, they measured the forces in the tibia. So this is the picture that you already know. This is the coordinate system of the tibia. So if you see here in red, this is the coordinate system. Z is in direction of the tibia, and this here is the X direction. So it's backwards. But what is the coordinate system of the femur? It's the green one here. So this is in direction of the femur and in the back. So if we measure forces in the knee joint, we always, or in every joint, we always have to say in which coordinate system the forces are measured, because this is the calculated forces during the same squatting for the femur. So you can see this shape maybe is a little bit here, you can see it here, but in this case it's the blue line, and the blue line is the x-axis. So in this position, for example, the force is directed for the, in the femur, it's more in the x-axis than in the z-axis. Why in the tibia, it's the force in the z-axis. And also the the z direction is completely different compared to the z direction in the tibia. So if we measure, if we calculate, or if we present data, measured data in the knee joint, we always have to define in which coordinate system we have measured this or we present the data, just as a side mark here. So what was the problem? Yeah, measure some data in the body. What is the solution? Until we cannot directly measure this, we should use, or we can use, unfortunately, computer models to do that. What else? And here I would like to show some videos. I think it's 5 or 6, which we have already developed here. Maybe you can see this new workstation here in the back. You can see one of our colleagues, Andreas, and he is doing a squatting movement. And as you can see, we have a new virtual reality possibility, so we can directly live stream the movement that we are measuring with the Qualisys system directly via the Qualisys and via our Myonado into this virtual world. What have we done? For example, we tested the function movement screen. This is a hurdle step now of a subject. He's now standing on the force plates here in the lab and doing this hurdle step. It's a virtual hurdle step, and this is the simulation with our Myonado. It's a different kind to visualize that. Now you can see which muscle is active in which situation. This is the same, but now in a different visualization. So this is now a visualization of our open lab where I'm in at the moment. You can see the cameras. You can see also I think it's quite the same. So in the back, it's nearly what you see here in the visualization now. And we can shift, so we can animate which muscle is active during which situation based on our calculations. Then it's a lunge movement. Now, again in that other environment. So you can see also the visualization of the open lab. And we can also change the visualization. So now we are in a gym. So this is possible to change that and to visualize the surrounding that you would like to show. This is the rotational stability. And with that, I would like to thank you very much for your attention. Hopefully this is working now. Bam. And this is maybe similar, but not the same. Thank you very much for your attention and to the one and only team of the Wagner Lab. Thank you very much. And I hope maybe you enjoyed a little bit and maybe you have the one and not only question.
Okay, thank you very much, Heiko, for that really nice lecture. Are there any questions from the audience? I see Mona.
Thank you, Heiko. I have no questions, but just thank you.
Thank you for the thank you.
I see Rosemary.
Yes, hi. Heiko, thank you. It was nice, very nice talk. Could you go back to the slide where you showed the muscle activation patterns that the OpenSim model showed? Or that
The OpenSim model showed. Yeah, I can, yeah.
Oh, okay.
But I use my lens for that. One second. It's here. Come on. So.
Oh, I can't see it yet. Yeah, because they kind of predicted that the forces in the knee were lower, but they also predicted lower muscle forces, right? Oh no, they predicted
no, it's vice versa. So the dotted line is the simulation, and this is the measured.
Okay, so yeah, because I mean, you would expect that if they have measure higher forces in the knee joint, that they would have also simulated higher forces, right, based on what you presented at the beginning.
Yeah.
So this is really strange then.
Yeah, but sometimes you have higher forces like this here.
Okay, there were some also.
Or here maybe, and.
Yeah, but in general, the EMG is much lower, right? With the exception of the biceps.
Or maybe this is, I don't know whether they showed the muscle activation, but they have also measured maximum voluntary contractions. So I have to check that in the paper whether this is in both cases % of maximum voluntary contraction or if the activations are only shown as the pattern. I have to check that.
Okay. Yeah. Well, at least the Miata looks better then.
Yeah, because I haven't, I have to, for the paper, I have to normalize the measured EMG to the MVC, and then maybe it's possible to compare the muscle activation of our simulation with the activation in the, but we don't, I think I really don't want to do that. I'm more focused on the pattern than on the absolute value itself, because even though we know a lot about the sixth subject, we don't know what is the isometric force of his rectus femoris muscle. So this is an assumption, and based on that, also the percentage of the activation is an assumption. So I think to show that the pattern is okay, but to really compare the activation, there could be a difference.
Okay.
Heiko, this is what I was going to ask. What is, in your opinion, what is more reliable in this model? The timing of muscle activation or the the shape of the muscle activation?
So if we are focusing on the muscles,
Yes.
I must say it's the pattern, the shape, and for the timing, it's if you neglect the electromechanical delay, for example, then you can also check for the timing. But if you would like to see something in 20 milliseconds or so, or 50 milliseconds where the electromechanical delay is on, then I think you have a shift. This is not here in our model. So there are some models we can account for that. But at the moment, we only calculate the activation. So there could be a difference in the timing, but the shape should be the same. This is what I would like to have.
And what kind of information do you have about the patella forces and the tendons?
From the experimental side, you mean?
No, from your simulation.
From the simulations, yeah. So so we can, at the moment, I can calculate the force in the tibia, the force from the tibia on the femur, the force of the patella on the femur. We can calculate, but I haven't done that at the moment. Yeah, so you have to use the patella tendon force and the quadriceps tendon force and calculate this. Then you have the force of the patella on the femur as well. We haven't done, or I haven't done that at the moment, because at the moment I was more focused on the force between the femur and the tibia.
Okay.
But it's possible to calculate that now. For example, in isokinetic machines.
Yes.
Okay, another question. Mark, do you have a question?
Yeah. I was interested. So what do the OpenSim people tell about their simulations? Do they think it's a problem that they're factor 2 wrong, or do they think it's really good? And do they tell why they think it's wrong?
They said that it's that it's, as you can see, generic musculoskeletal simulation. So if you the conclusion is, if you just use OpenSim, make a calculation, then you don't get the right values. So you have to change something in the model and to include that. And it would be, so I don't say that OpenSim is a bad model. I don't never will say that, because it's really a very good one. So, and they already have more complicated, much better knee joint models than I have used here at the moment. And if you include these knee joint models into the OpenSim and compare it with the CAMS-knee data, then you will get, I will assume that you will get much better results. But here the paper is the capacity of generic musculoskeletal simulations. So then you will get this not so good results, I must say.
Okay, another questions.
I have a question.
Walter, hello.
Okay.
What a pleasure. Heiko, I was wondering about attention. Could you add something how attention could change the muscular activity in your model? Because we know when we have attention for a, I don't know, when we have to jump to make a block in handball and so on, we also have a pre-activation of those muscles that we will activate. So is it possible to add a kind of attention parameter or something related to pre-activation in your model that is not only related to muscular activity?
So if you can tell me the relation between attention and muscular activity, then I can include that in my model.
Okay, I have to find. I don't remember now by head. But I assume this is, I'm completely convinced that exists. But then you are telling me that it is not possible to add something that is not measurable in the model.
Why did I tell that?
No, this is I'm trying to interpret your comments.
You mean the comment that I don't know whether I get you right. So the comment about physics, that we need to have observables and something like this, or the comment that you have to give me the relation between attention and muscle activation?
No, I was more related to the not physics part, but more related to the subjective activation of the muscle that could be activated by attention or another visual information that you cannot measure this when you are doing muscular activity or jumping, but you know that there is a pre-activation based on attention enhancement or decrease.
Yeah, but you can, the scientists in the psychological field, they are able to measure attention.
Mm-hmm.
And we are also able to measure muscular activation. But then you need to have a relation. It must not be directly in a force law, but minimum a relation where you say, okay, how is the attentional focus maybe it's the first, this part, for example, 1 second, where our simulations don't fit with the measured ones, where I said, okay, when I start the squat and I have a new prosthesis, maybe I start with an increased co-activation of the muscles to secure that knee joint, and then I can release that after a while, and then it already fits to our simulation. So maybe this here could be simulated better if we have something like a model which describes the fear for pain, or I don't know what. So you can say it's attention or something like this, or some psychological factors to also have a prediction for these areas. Yeah.
Okay.
If it is just an interpretation of mine that this is because of that co-activation, but if that is true, then maybe it could be interesting to include that.
Nice, thanks.
So, Mark, do you have another question?
Yes, I was because if I understood you correctly, you promised to tell something about this co-activation, and I thought maybe you were going to show us some of the.
Yeah, that's right. So the question is, for example, this is biceps, no? Maybe, so, first of all, they have only measured 8 muscles per leg, no? So there are much more in the body, so it's only an estimation now. And you can see here in this area, this very large activation peaks. So maybe this is the co-activation of the biceps in starting the movement, or also here the gastrocnemius, which is also a muscle acting at the knee joint. And you have here, for example, the vastus medialis, which is quite active and reduced.
That is your simulation.
This is from our, excuse me. So in the model, it's the only activation part is here in the gastrocnemius and in the biceps, what was measured. Yeah.
Okay, thank you.
Yeah, I don't know whether this is a possibility. It's just a guess. I don't know.
So I see Charlotte.
I see Charlotte. We all see Charlotte. Hello.
I see Charlotte's hand.
Hi. Yeah, thanks for the talk. So I was wondering, there's no way for Leonardo to be able to guess co-activation. Since it's using inverse dynamics, it can just estimate the total torque and force on a joint, but then would it be possible to figure out if the muscles are being co-activated, or would that have some influence that could be measured and that could be estimated, or how could that be done?
The Walter function.
Walter function, yeah, this is there are 2 possibilities. For example, for this CAMS knee data set, I was thinking about changing the optimization routine in our model to not only fit the calculated torque in the joint, but also fit the measured data in the knee joint. Yeah, and to see how whether we will get different activations here in the biceps or other muscles if we not only have to generate the force, the torques that we have measured, but also the forces in the joint. And based on that, maybe we get some increased activations then of muscles during that phase. The other possibility that we already have is that we have a co-activation factor, which is, we call that co-activation factor. So where we can just say what is the minimum active. So at the moment we try to minimize the muscular activation or the relative muscle force. We can change that to be minimum at that joint, for example, for the knee joint, to generate the whole the calculated moment. Yeah, this is the normal way how you can do it. And we can change that to say, okay, the minimum is not 0, the minimum is, let's say, 10% or 5%. And then the optimizer tries to fit the muscles according to the 5% value. And this will result in the end in a general co-activation. Yeah, but it's not a phase-depending co-activation. Yeah, it's because we don't have information about that from if we only have the external moments. So we can, for example, it could be possible to define a vector to say, okay, at the beginning it's 0, then we assume to have a 5% co-activation during a phase, and then we reduce it back to 0 or something like this. And then this vector would be used in the optimization process. So this could be maybe a possibility to account for that.
Okay. Yeah,
do you have a better idea than mine to do that?
No, it's really something I'm confused about. So coming back to a previous question, I don't know the relation between attention and muscle activity, but for example, fear increases co-contraction. So if you look at just standing people, gastrocnemius and tibialis anterior activity when they're standing on the ground, you mainly get gastrocnemius activity and nothing in the tibialis. But if you have them standing at the edge of a 5-meter high platform, then you start seeing activity in the tibialis anterior as well. So yeah, co-contraction seems to increase with fear of falling or...
Yeah.
Okay, I see Luis raised his hand.
Yes.
Do you have another question?
Yeah. In fact, it's not it's almost a question, but it's also a suggestion, because I was thinking, well, we have several ways to optimize the system, and you have to choose one. So, and I know that you are also working with the descending sensory information model. Yes. So, for example, just like Charlotte said, if you have fear, then you may change your. I would say that you can change your optimization method. So instead of using just one optimization model, you could have, for example, 3 or 4 different ones, and the descending information would be the weight of each one. So if, for example, you run minimal energy, minimal displacement, and so on, and you run all of them together, but then you use the sensory information to weight how much you're gonna use of each optimization, then you sum everything, and then you have the result. Because, for example, when we do it in the real life, well, we have sometimes we are optimizing the movement because of pain, because we are fatigued, or because we are afraid, or because we want to do it as fast as possible. So maybe we are doing everything together, but